affects the second law of thermodynamics? The speed. Surface area and the temperature difference. If I do not have a temperature difference, can I get heat to move?
No.
Nope.
No. We must have a temperature difference. That's correct. Good. Rocking it. How are we doing in time? Okay, so you guys ready for a break or want to keep going?
Keep going.
All right. All right, so the next thing we're going to talk about is we're going to talk about components of the air conditioning system and also the science that connects with them. So the first thing we'll talk about is a compressor. Here's how I draw a compressor. We're going to go to the lab here shortly and see one, and you get to see what I'm trying to draw. But it's called a compressor. Compressor, but in HVAC, everything has at least two names. Every component has at least two names. First name's a compressor, that's easy enough. The second thing it's called is a vapor pump. It pumps vapor. Two names, vapor pump, compressor. They mean the same thing. There's many styles of compressor. We'll talk about the simplest one first. Left picture, we have two cylinders here. And this cylinder, down here at the bottom, this cylinder here, is at the top. What's the difference between these two cylinders?
Volume.
Oh, I heard a lot of correct answers. One big difference is the volume inside of here. There's more volume, there's more space right here. Over here, there's less volume. So what we have is a volume decrease, but there's the same number of molecules here. The actual molecules are the same, but I put all these molecules in a smaller area. What I've had happen with that is the pressure increases, right? Pressure increases. This works with a vapor. Air is a vapor or a gas. Nitrogen, oxygen, all those are gas in vapor form, and we can compress vapors. What if I put a liquid in here? Can I compress that?
Depends on how much liquid you put in there.
Very, very slightly.
If it was fully top dead center, we cannot compress a liquid. If we try to compress a liquid, we end up with hydraulics. That's how we can make all that machinery move. We can move mountains with that because we try to compress a liquid and it moves hydraulic pistons. If we get liquid in a compressor, it will destroy it. Something will break. The valves will break, the piston will break, the connecting rod will break. Something is going to break. So we do not ever want to get liquid in here because something is going to break. When you ever seen a car or heard about a car being hydro-locked, it gets water in it. If you get water in it, it fills that cylinder and you try to compress that liquid and something will break. Hopefully it just shuts down, but usually it means something's breaking, bending, giving, bad stuff's happening.
Mm-hmm.
That's the one you put on Craigslist.
But when you say vapor, isn't that water in the form of a gas?
It is water in the form of a gas, but because it is gas, we can now compress it.
That's why gas leak, it's vapor.
Liquid state, we can't. Because it's gas, we can.
So if you want to get water out of there, you can heat it up.
Well, yes, but we have to have a place for it to go. And where are we at? If it's a car, where is it at? Are both valves closed? Are we in a compression cycle? Are we on an exhaust cycle? Are we on an intake cycle? There gets to be several things. As far as what we're using for a compressor in our systems, there's just an intake valve and an exhaust valve. So intake valve, it pulls in gas. Exhaust, it squeezes it into a smaller area and pushes it out. What this compressor does is, one, it moves the refrigerant. It moves the refrigerant.
I guess we don't ask you how to spell refrigerant.
What's that?
I guess we don't ask you how to spell refrigerant.
No. In my head, sounds great.
It actually looks right.
I just let my hand do it. Whatever it writes.
So the compressor, what it does, it's sucking in low pressure vapor. It sucks in low pressure vapor. So we're going to have a pipe called the suction pipe, and it's going to be a larger pipe sucking in low pressure vapor. On the other side, there's going to be a smaller pipe where it's pumping out a high pressure vapor. I'm going to use blue for low pressure. I'm going to use red for high pressure. High pressure vapor, low pressure vapor. It is a vapor pump.
Or hot and cold.
No. And that's gonna be complicated. So we're just gonna think of it as high pressure and low pressure because that's gonna get obscured by tomorrow. I'm gonna throw hot and that's gonna be completely out of it.
Fantastic.
Is that our desired goal to make our pressure high?
What's that?
Do we want high pressure?
We do want high pressure. It's a great thing for high pressure. Why? I'll show you. This and this and this and also this. All right, so molecules, heat, energy, motion, all ties together. It's going to be hard to talk over this, so I'm just going to do the demonstration, then I'll explain it afterwards. So the BBs represent energy, or molecules, atoms. And the atoms are moving around and they're bouncing across the edges and every surface in there. That's how a gas works. It's bouncing off of everything all the time. If I increase the energy in that, whether it be pressure or temperature, the molecules start bouncing faster. So if you see the styrofoam, if you think of that representing pressure, the molecules, as there's more energy involved, they're moving faster. So as they're moving faster, it's bouncing off the surfaces more times, constantly bouncing off, which is pushing against the sidewalls, which is increasing the pressure. So if I add heat to a sealed container, the pressure is going to go up. Also, if I take and reduce the volume, the pressure is going to go up, but also the temperature will go up. And there's several laws related to that. To save us time, we're not going to define them all, but there's Boyle's Law, Charles' Law, Law of Perfect Gases, Gay-Lussac's Law. There's a whole bunch of them all tied together. But all of it really means when temperature goes up, pressure is going to go up. And if you decrease the volume, pressure goes up. If you increase volume, pressure goes down. It's all related to the same stuff. So what I have here is a little demonstration to help show some of these concepts. So this is in Celsius, because I got this in Europe. Had it shipped from Europe. Couldn't find it in Fahrenheit. Too lazy to change the thermometer over. So it's in Celsius, but it doesn't matter what point it's in, you still get the idea. I'm going to seal this off. So this chamber is sealed. Here's the pressure inside the chamber. Here's the temperature inside this chamber. A compressor is going to decrease the volume. What's going to go up?
Temperature.
Temperature and the pressure. So if you guys can see it, It's much more dramatic if you do it fast. I've been talking about putting a drill in this for several years now. Hasn't happened, so I'll try to do this as fast as I can. Don't make fun of me. Can you see it change?
Yeah.
Does that become more difficult to do?
Spikes right there at the end.
Yeah, because we got the more we get down those molecules, the more we squeeze them, the bigger the jump's going to be. So this is what's happening in our compressor. As we get to right here, the temperature and the pressure both increase. Pretty cool, huh? On this other side, when we get back to this side, it's going to do this. Temperature and pressure decreased. Pretty neat, huh? The job of our compressor, suck in low pressure vapor, pump out a high pressure vapor. Which pipe's going into the compressor?
The blue.
The blue, low pressure. That's going to be sucking in. Which pipe's going out?
Red.
Red. It's going to be the smaller one that's going to be going out. All right, now let's go to the lab. Let's take a look at this. On the compressor though, there's still just one pipe in,
Still one in, one out.
one out. And commercial is the same thing as residential, it's just that we add more components to manipulate that refrigeration cycle.
Okay.
Sorry.
So then, is there any other kind that have more than one, or is it, it'll always just be one in, one out?
Oh, when you get to industrial,
Yeah.
sometimes you'll have 2 or 3 pipes coming in.
And then
And
still
then
one
2
coming
or
in,
3
or
are
two
coming out.
So it's the same, if you increase the number coming in, you have to increase the number coming out.
Not necessarily. I have seen them where you had multiple ones coming in, but it's like a manifold system.
Okay,
And they
yeah.
bring them in, and then they'll stage. So it goes into one cylinder, out of that cylinder, into another cylinder, out of that cylinder.
And see if it's accepted.
Yeah, in series.
Alright.
So it is. When you get to cascading systems, they'll do that sometimes too. So big pressure differences, but you get complicated systems. You don't see it very often. It's
Yeah.
a rarity.
I'm
But
assuming you
it does
probably
happen.
Yeah, you probably see something crazy different.
You'll never see it all. There's just. But if you understand how it's working,
Yeah.
it doesn't matter what it is. You'll get a concept of it. One person. So this line that comes out of the compressor. 2 names. Can't have just one. 2 names. So one of the names is called a discharge line. Discharge line. Discharge just simply means coming out of. So this line is coming out of the compressor, so it's a discharge line because it's a line coming out of the compressor. Discharge line, that's one of the names of that line. It's the shortest line in the whole system. The other name it's called is a hot gas line. The refrigerant in there is going to be a gas or a vapor. And that gas or vapor is going to be hot. And it's in gas form. And it's hot, and it's a line, so they call it a hot gas line. Or some people call it a discharge line. Some people can call it a discharge hot gas line. The more people come up with names for stuff, then the more stuff we have to learn. That's why I tell people, don't make new names for stuff that's already there, because there's plenty as it is. So that line, discharge line, also is a hot gas line. It's the name of that line. It's a short line. The state of refrigerant that's inside of that line is a high temperature, high pressure, superheated vapor. We're going to talk about what superheat means later. We're not ready for that yet, but it's just, if we go ahead and put that word in there now when we get there, it'll make more sense. So the refrigerant coming out of this compression, that smaller line, the discharge line, it's also a hot gas line. The refrigerant is a high temperature, high pressure, superheated vapor. So far so good? It's the shortest line of the whole system. But from there, that line ends up to a component, and this is one of our key components. The first key component is a compressor. Next key component is called our condenser. Condenser, and the job of the condenser is to reject heat. It's our condenser. It's rejecting heat, getting the heat out of the refrigerant. So where do you think the condenser is going to be located?
Outside.
Outside. That's exactly right. Outside. Rejecting heat outside. Now when you looked in that box, you saw the compressor in the center of that box. But on the outside of that box, all around it, that was your condensing coil. It's pretty much just a bunch of copper tubes with aluminum stuck to it to increase surface area. Sound good? All right, so I'll show you what one looks like. A small section of one anyways. I'll pass it around, everybody gets to see it. But this is just a small cutout piece of a condensing coil. The refrigerant's running back and forth in these tubes on the inside. On the outside are moving air across it. So we're having heat exchange. The refrigerant has to be warmer than the air outside. Remember somebody said, do we want to increase our pressure and temperature? Yes. What I want to do is increase the pressure of this refrigerant and increase the temperature of the refrigerant so the refrigerant is hotter than the air outside. If I get this where it's warmer than the air outside, what's heat going to want to do? It's going to want to go to the cooler air outside. Now all of a sudden 115 is cool. Compared to this, all the heat's in here. We want to get that heat to leave, so we got to make this warmer than the air outside. So the hotter it is outside, the hotter I got to get this. So now, and I don't want to add heat to it, I want to get the heat out of it that I already have. So I do that by increasing the pressure. By increasing the pressure, I increase the temperature. Now the heat is wanting to leave the refrigerant to get outside. And I'm moving air across this, so the heat's leaving the refrigerant through the coil into the air. So the air is coming out of the unit
Cold.
warmer. The air is coming out warmer because the heat's leaving the refrigerant going to the air. The refrigerant coming out of this cooler, less heated. Make a little bit of sense? Pass it around. So the refrigerant's running, and this just represents the pipes going back and forth. Refrigerant's inside, air's on the outside. We move the fan, we move the air, continuously move the air through that. What happens if I stop moving air through this?
Too hot.
It's gonna overheat, it's getting too hot, just like your car. If I cover the radiator of your car up or shut the fan off in your car on a summer day, it still wants to reject heat, but without moving air across it, it's gonna overheat very quickly. And the same thing with the unit here. We wanna keep that air moving through it. So when you look through, you saw the fan blades, and you saw the compressor underneath. That fan is what's moving the air through that condensing coil. Make sense? You wanna go look at it again, or you can picture it?
Picture.
Picture it? Okay. We're gonna be in and out anyway, so next time we go out, you can take a look at it for sure. So we're rejecting heat. Now there's several details we gotta discuss here, but we're gonna circle around to it later. From there, the refrigerant leaves that coil in a small line. This line has a special name. Liquid line. And the good news is, it's only got one name. Liquid line. The liquid line. The state of refrigerant in this line is a warm, high pressure, subcooled liquid.
Subcooled also to be explained later.
Yes, sir. Subcooled and superheat, we'll have to wait. It's a little cliffhanger. To be continued. Tune in tomorrow.
Same bad time.
So if you fill it here, what's the name of this line?
Hot gas.
Hot gas line. And now if I was to then grab the line here, it's going to be warm to you, to your feelings. This will be hot and this will be warm. But according to the refrigerant, it's a subcooled liquid. We'll get there later. So which one will be hotter, this line or this line?
The hot gas one.
The hot gas line. What happened is the refrigerant got rid of some of its heat, but it's still going to be warm right here to you and your feelings. Okay? So far, so good? As we flow through this cycle, we're going to have to go through a little accessory right here. This is not a major component of the refrigeration cycle, but it is a component that you should always have. And this component will have an arrow on it. Should also probably put my arrows here. This component is called a liquid line. What line does this go on?
Liquid line.
Liquid line. So we call it a liquid line filter dryer. Can I put this liquid line filter dryer on the hot gas line?
No.
No, because it'd be called a hot gas line filter dryer if it was. Cannot go here because there is no liquid here. Here there is liquid. The refrigerant condensed into a liquid, which we'll explain later, changed state into a liquid. Here, liquid refrigerant is flowing through this. It filters the refrigerant. It also is a dryer. Anybody ordered anything and you got those little packets in there that say do not eat?
Mm-hmm.
What's in that little packet that says do not
Silica
eat?
gel or silica
Silicate
dust
or a desiccant. What it does, it absorbs moisture. It absorbs H2O. So there's liquid refrigerant, it's not absorbing that. If there's any H2O, any water in there, ideally that will absorb and hold that water so that water's not running through the entire system. It also has a filter effect in there, so it's taking some contaminants out of that unit, helping filter it. So I got that to pass around so you guys can see it. So the first one I'm going to pass around is a desiccant material. This is what the stuff's made of. It came out of a commercial unit and I cut it down to make it smaller. I've been passing this around for many years now. A lot of people have touched it. Plus, I'm sure the desiccant's probably not good for you, so please do not lick it. More than once, I've had to remind people of that. So just making that clear. So I'll pass that around. Here's what it looks like on a residential system. This one is a biflow, so it's got arrows in both ways. But usually there's just one arrow for one direction. So this is what it looks like. I'll pass it around. And once it comes back around, you can see if we'll put it back on this cabinet. And there's more. I have one that's cut open. Here we go. Here's one that's cross-cut, so you can see what it looks like on the inside. You can see the filter material, and you can see the desiccant material. So that is a liquid line, filter, and the dryer. You don't want to drop those. They make two kinds, well they make a lot of kinds, but two basic kinds. They make one that's a solid desiccant, like a rock like that, and they make another one that it's made with BBs in it, and a spring holds them together. The solid ones like that, if you drop it, even though it's in a metal case like this one, you drop it, it'll crack it inside. And that dust will end up going through the refrigeration cycle and trashing the system. So you never want to drop them, and if you do drop one, throw it away. Don't try to put it in because you're going to do more damage than it's worth. I prefer the ones that are like BBs because they have the spring, and if you drop those, they'll take the hit and it won't break on you. And they're much more dependable. So it looks like a solid rock, but it's porous. The refrigerant flows through that.
You're trying to make your liquid dry?
Not make the liquid dry, pull H2O out of it. So it's only absorbing the H2O, the water, taking any water out.
Like oil in a motor, you don't want water in the oil.
Yes, exactly. You're not, if I was to have a water, they make water separators for some of those fuel lines, especially with diesels. So even though they're both liquid, it's only taking out the H2O, keeping the rest of it liquid. Good, thank you for that. So any questions about that? If it has an arrow, it's always pointing away from the condenser towards the next component we're talking about. It must be in that way. It's going to be on a small line pointing away from this outdoor unit. Must be pointing away from it because that's the flow of refrigerant. And there is one more style. I should go ahead and talk about this now before we move on. Sorry. One more style that you do see.
So the refrigerant becomes a vapor?
Oh yeah, we make it change state. We're going to talk about it today. We're just not quite there yet. We'll just keep going the same way. This is a component I'm not going to talk about yet. We're not ready for it, so pretend that's not there. This, it'll look like a hot dog. This is what we're going to be talking about. This is also a liquid line filter dryer. Some of the factory ones use this. It does the exact same thing. It just looks different. So I'll pass it around so you can see that.
So you pump the refrigerant through that substance and that makes it drier, less liquid,
Not less liquid, takes moisture out. H2O.
or less moisture, I mean less water out of it.
Yeah, gets the water out. And a very small amount. These aren't holding very much. So when we're talking about water, I'm not talking about water you can see. I'm talking about, like, there's water in the air right now that you can't see. It's humidity, even though it's low humidity, there's still moisture in the air. That moisture, when you open this lines up, that moisture collects inside of these pipes, and you have to get as much of that out as possible. But you can't get it all out. So that last little bitty bit that's left, we'll collect in here. I mean, it's such a small amount that we'll collect in there. You have to make sure when you're doing work on it, you get everything out that you can, because it's a very small amount that can capture. A lot of people are like, oh, just do whatever because it won't matter, that'll catch it all. It's not how it works. These will last for 30 or 40 years. They'll last a long time. But once you open the system for any reason, if you open it for any reason, I hooked it up, I installed it, I turned the system on for 2 minutes, and I shut it off, gotta fix a leak, do something else, I have to take the refrigerant out, I gotta cut this guy back out, put a brand new one in. So if you never open the system, you don't have to change it. But if you open the system, then you must change that filter dryer.
Is that the only thing that can make it go bad?
No, there's many other things that can make it go bad. There's people that put their gauges on, had contaminants in their hoses, they put them on this unit, now there's contaminants in here. Also, people that they didn't pull a good vacuum, it caught all the moisture it can, but now the moisture that's in there turns to acid. The acid starts eating away the compressor and the copper pieces, and those will start building up and clog it up. Compressor failures, running the unit without the fan motor causes high pressures. This will break down. All those contaminants can clog up in here, and you can also have that issue. And we'll talk about how to check this later on, but there's several things that can cause it to go bad. Yep. So it's just protection.
Just out of curiosity, if somebody, let's say the difference between Florida and here, the difference in moisture in the air, do you have to install a different size, or it doesn't matter
If you do it correctly, your stock, we use a gauge when we're pulling a vacuum, when we're cleaning this out, and if we do it correctly, if we get to the correct number, it doesn't matter where you're at, you're there. So, it will take longer to get there if you're in Florida on a humid day though, than it would here. So this dryer we change anytime we open the system up. If we don't open the system, there's a way to check it to make sure it's still good, but usually it's not as part. We have to, we need to go change it every year. There was this one lady, she called me and said, it's time for me to change my refrigerant and change my dryer. It's like, man, what are you talking about? The last company said I had to come and change that out every year and change my refrigerant because it expires. Like, no. Refrigerant should never wear out. That dryer should never wear out either. So, unless if it is, there's a problem and you got to find what's causing it. The refrigerant's going through that filter dryer, and then we come to our next component. Our next component has 2 names. Imagine that. This is the symbol for the component, but it's not what it looks like. This component is called a metering device.
So it's not a railroad crossing.
Not a railroad crossing. So I did it in black instead of the yellow. Or yellow white, that's what it is. Black and white. Can't even remember. Metering device has 2 names. The other name is called an expansion device. Metering device, also known as an expansion device. All this really is a hole, or an orifice. Like they call them fixed orifice or a fixed hole. If I have high pressure refrigerant running to the side and a very small hole there, is all that refrigerant going to be able to go through there at the same time? No. It's very important that we have this component because it has to be there for the compressor. The compressor has to have that metering device because if I'm pushing refrigerant, I need to have a small hole for it to back pressure against. If I didn't have the metering device, the refrigerant would flow free flowing and I would never build high pressure up. And if I never build high pressure up, I can never get my temperature up to get the heat to leave it. Imagine turning an air compressor on with all the valves open. No hoses on it, or if you had hoses, all the hoses were just cut and and you turned it on, is it going to build pressure?
No pressure.
It's going to be running, but it's not going to build pressure at all. So here we need this metering device to even be able to build up high pressure. So we're pumping against this metering device to build the high pressure. Does that make sense?
Mm-hmm.
On the other side is a beautiful, magical thing. Think of taking a water hose and squeezing the end of it. You're going to build pressure on one side, and the other side you're going to have less pressure. So what this metering device does is it meters or restricts the flow of refrigerant from a high pressure liquid to a low pressure mixture. There's more words we're going to add there later, but it'll just cause confusion now, so we're going to skip that. So here, I go from a high pressure immediately to a low pressure. If I take this cylinder and I put it here into a vacuum, I increase my volume, I would allow the gas inside this volume to expand, right? Expansion device. What is my pressure doing? Lowering. What's my temperature doing? Lowering. So here, as I drop my pressure, allow for expansion, I'm also dropping my temperature. And if I drop the temperature of this lower than the temperature of the air, what's going to happen?
Cold air.
It's gonna feel cold.
Heat transfer. Heat's going to leave the air and go to the cooler refrigerant. So for example, let's say the air temperature, 75 degrees Fahrenheit. Let's say the refrigerant temperature drops to 40 degrees Fahrenheit. Is there going to be heat transfer? Yes. Especially if I run it through a coil with aluminum fins to increase surface area. There's a temperature difference and there's more surface area. The heat is going to leave the air and go to the cooler refrigerant. So the air is going to be cooler coming out. I've taken the heat out of the air and put the heat into the refrigerant because I've dropped the pressure. You had a question back here?
Or so like the valve?
It's good question. Let me show it to you. They do make some with valves. The most common kind, I'll pass them around. Sorry. All right, so these are two different styles in this package. There'll be some kind of a fitting or connection, and inside this is an orifice. It's called a fixed orifice. It's also called a piston, but it's a fixed orifice or fixed bore metering device. That hole in the center is the metering device. This whole piece is the metering device. That hole is a special size, and that hole has to match the compressor. They have to match because they have to work as a team. If this hole is too big for the compressor, it's going to let too much through. If the hole's too small, it's going to build up too much on this side. Very precisely sized hole, and here is another one, a different style. The brass is larger, but the hole is the same size. It's a fixed, it doesn't change, it never changes its size. Pass that around. They make another one that's adjustable. It opens and closes with conditions. So it's got a bunch of extra parts that we're going to talk about later. We're not ready for it. We will get there and understand it, but right now we're not. This, the size of the hole, has pins that move inside, so it opens and closes with conditions to adjust its flow. This is the one I like, because it's awesome. They make it with awesome sauce. We'll talk about how it works later and why it's so much better later. But these are the two most common styles you're going to see. So let's run through this cycle real quick, and we'll go into the lab, look at it. I drop it from a high pressure liquid down to a low pressure mixture. And as that refrigerant turns to this coil, the temperature of that refrigerant is lower than the temperature of the air. The heat leaves the air and goes to the cooler refrigerant. And if heat's leaving the air, what's happening to the temperature of the air? It's getting cooler, it's dropping. So where'd the heat go?
Into the refrigerant.
Into the refrigerant, that's exactly right. The heat's in the refrigerant. So this component right here is one of our 4 components. This is called the evaporator. And it's absorbing heat. This line has 2 names. It's called the suction line. It's also called the gas line. Some people prefer to call it a suction gas line. Sums it up. The refrigerant inside this line is a low temperature, low pressure, superheated vapor. We'll talk about superheat later. It's important.
Suction line, right?
Suction line, also a gas line. Or just simply a suction gas line. Sometimes easier.
So it's low temperature, low pressure, and then
Superheated vapor. It's weird. Once I explain it, hopefully it'll make a lot more sense. Hopefully. If I do my job correctly, it'll
Now
make more
what's
sense.
going on inside the compressor, sort of like what you're doing now, right?
Yep, it just decreases the volume, which increases the pressure, which increases the temperature.
Okay.
Right, so far so good? All right, so we're gonna go to the lab and look at this in just a minute, but I wanna run through this cycle real quick. So here, the refrigerant's coming through this meter device, and I dropped the pressure. So therefore, by dropping the pressure, I drop the temperature. Now the temperature of the refrigerant is lower than the air temperature. So heat is leaving the air, going to the refrigerant. I have to keep air moving through this. The heat is in the air. So if I move the air through this and I take the heat out of the air is coming back into the room cooler. We've taken heat out of the air, but where did the heat go? Into the refrigerant. Here the refrigerant still, to you it's a low temperature. It's for sure a low pressure, but according to the refrigerant it's superheated. We'll get to that later. It's a gas. It goes into the compressor. We push it to a smaller volume. The pressure is going to go up. So when the pressure goes up, what else goes up? The temperature is going up. So now we have the temperature of the refrigerant is higher than the temperature of the air. What's the heat going to want to do? Escape. It's going to want to leave the refrigerant, leave and go to the air outside. Once we get the heat out of the refrigerant, we're in liquid. That liquid sends it through our filter dryer to our metering device, which restricts it from a high pressure back to a low pressure. Now we have a pressure drop. We have liquid coming in. That liquid changes state to a vapor. Superheated vapor comes back. So the heat right now is in the air. What's the temperature of this room? Is it 72.
Room temperature.
Room temperature is 72 right now. 72 degrees. So I say the temperature of this room is 72 degrees. The heat, there's still heat in this room, right?
Yep.
Yeah.
There's a lot. Let's say 460 plus 72, that's a lot of heat. There's a lot of heat in the room. So the heat is in here. It's like, yeah, this is good. We like this. This is great. And then the heat is in the air, and the air gets pulled across the evaporator. And the heat's like, whoa, it is so much cooler over here in this evaporator. Let's leave the air and let's go to the refrigerant. Let's go to the evaporator. So the heat leaves. It starts leaving the air and the heat starts jumping in the refrigerant. Man, this is so much better. 40 is rocking. This is awesome. We love it. And the heat is getting all the heat we can get. Everybody, all the heat's jumping in here. Jumping in as fast as they can. So the heat's now in the refrigerant. The refrigerant's like, yeah, this is awesome. And it's being sucked back to the compressor. Yeah, this is great. And then we get to the compressor. Now imagine everybody in this room being squeezed into this corner of a section this big. Okay, all of you guys are squeezed as tight as you possibly can in this corner. Sounds good, huh? You're going to be a lot of pressure, and the temperatures are going to be building, and it's very unhappy. Very much unhappy. So that's what's happening in the compressor. It forces all that heat to pack in together, and it does not like it. So now all this heat's packed in here together. Let's say it's 115 degrees outside. So the refrigerant's going to be at least 135. Oh, this sucks. This is horrible. We were tricked. This is wrong. This is BS. We don't like this at all. And so we pump it through the outside. Now the refrigerant's all there, packed together, 135, miserable, unhappy. And then they see, oh, look, it's only 115 outside. That is way cooler. Let's leave this hot refrigerant and go to the cooler air outside. So the heat starts jumping out as fast as it can. Everybody, let's go. And the heat's leaving the refrigerant as fast as it can, and it goes into the air outside. Once the heat's out of the refrigerant, there's still some heat in here, but they're all packed together. And then it comes over here, and then it all spreads out. They got plenty of room. Now we can absorb more heat. It's cooler. And then once the heat gets over here, we trick it again, push it together. Trick it to leave to go outside. So the heat's all together, the heat leaves the refrigerant, goes to the air outside. Oh man, 115 is so much better than the 135. But now the heat's outside, and it's looking through the window going, man, it's 72 in there. It is so much cooler in there. We got to get back inside. We got to get back in there. So the heat starts fighting its way, crawling through the walls, crawling through the glass, crawling through the ceilings, crawling through the floor. The heat's fighting. It's getting its way back in. The more insulation there is, the more bounces there are, the more it's trying to keep it out. But it can't be stopped. The heat is coming back in. And that heat gets back inside. It's like, yes! 72 degrees. This is awesome. And the more heat that's coming in, the more that temperature starts to go up. 73, still awesome. So it's great. Come on in, guys. The heat's in there. And then we pull the heat through the evaporator coil. By having a lower temperature, we trick it. It leaves the air, it goes back to the refrigerant, it's happy, it's rocking, and then it's like, oh man, we're outside again. We got to get back inside. That's the refrigeration cycle. That's what's happening. To get heat to move, we must, second law of thermodynamics, must have something colder for it to go into. So the evaporator coil must be colder. Over here, if I want it to leave to go to the air, I have to get the air colder. Well, I can't control the air temperature outside, but I can control the pressure. And if I increase the pressure, I can increase the temperature, and I can get the heat to leave the refrigerant to go to the air. So now let's go to the lab. Let me show you these metering devices, what they look like on the unit.